Hi everyone, and welcome to our discussion on atmospheric thermodynamics. We're talking about the thermodynamic equation. This is our last topic in atmospheric dynamics. And what it says is that a local change in temperature of a parcel results from three things. Number one, the horizontal temperature advection. Number two, vertical motions. And number three, diabatic heating. And we talked about vertical motions and also diabatic heating, and I think you probably know what temperature advection is already. So what we're going to do is we're going to take this equation and simplify it. Number one, we're going to get rid of the diabatic heating term. Diabatic heating and cooling occurs when there's condensation, when air is touching the ground, there's conduction, or there's radiation that's being absorbed. So we're going to look at only adiabatic motions. So we'll get rid of that term. We've got to make this equation simpler. So that leaves just temperature advection and also vertical motions. So what we're going to do now is we're going to solve for omega. This is the vertical velocity. So to do that, we have to put all the terms on the other side that don't have omega in it, and then divide both sides of the equation by P over R times sigma. When we do that, omega's on the other side. There's a whole bunch of stuff in the top of the equation, and then something with sigma in the bottom. And the last thing that we're going to do is we're going to assume that temperature changes only occur from advection. So we're looking at only advection. So if we get rid of that term, the equation looks a lot more simple. Now, this equation says that omega is a result of two things, either in the top temperature advection or in the bottom static stability. So this is another method for figuring out vertical velocities. If you remember from our previous videos and our previous discussion, we came up with a way to figure out vertical motions in the atmosphere using convergence and divergence. We called that the kinematic method, but we had problems with that method. So we came up with vorticity to help us figure out where there's rising and sinking motions in the atmosphere. This is another method of figuring out where there's vertical motions in the atmosphere, and this method is called the adiabatic method. So let's delve into this. Let's take a look at this in a little bit more detail. So you know that when there's warm air advection, the equation for temperature advection is minus V dot del T. Now this is the horizontal temperature gradient, so that's, or horizontal temperature advection, so that's why we have the H next to the del. Now, remember that when there's warm air advection, that term is positive. If you look at the equation that we have now, there's no minus sign in front of that temperature advection term. So it's a little bit different. So when there is warm air advection, that means that top term is actually negative. And if the top term is negative, the whole right side is negative, and that means omega is negative. And you know that when omega is negative, we have rising motions. So what this says is that when there's warm air advection, you have rising motions. And that's what we normally expect. For example, with a warm front, as air rises up along the warm front, you have warm air advection at 850 millibars. There's your warm front down at the surface. This is on the East Coast. And there's lots of clouds and lots of precipitation. So this works. When there's warm air advection, you have rising motions, and you'll get condensation and precipitation. Now remember, the thermodynamic equation, the way we solved it, does not include diabatic heating or cooling, but it gives us an indication of where there's rising motions and what can happen down the road in the future. Let's do cold air advection. So with cold air advection, normally minus V dot del T is negative. Now we don't have that in the top of our equation, or omega equation, we have no minus sign. So that means that V dot del T must be positive for cold air advection. So that makes the whole right side positive, and that means our omega must be positive. So a positive omega means that we have sinking motions in the atmosphere. So this is what happens behind a cold front typically. We have cold air advection. Cold air advection is very dense and air tends to sink. That's what you see here at the 850 millibar map. You see very strong cold air advection. With that, you have clearing skies, big high pressure system, diverging air at the surface. And if you take a look at all the METARs in the area, for the most part, skies are clear across that region. So this is your adiabatic method for figuring out vertical motions. It deals with the thermodynamic equation. It says that when there's warm air advection, air rises. When there's cold air advection, air sinks. Now, what about this P sigma over R? That deals with the static stability. That is always positive. The atmosphere is always statically stable. But if the atmosphere is more stable, then that term is big, and that means your omegas will be smaller because it is in the denominator. So I hope that gives you a little bit of insight as far as what happens in our atmosphere. Warm air advection causes rising motion, and cold air advection causes sinking motion. And that is from the adiabatic method.